Hello and welcome to 11th lecture of course on data-enabled tribological engineering from experiments to predictive models. Topic of this lecture is elastro-hydrodynamic lubrication. This lecture is a bit difficult because it requires a lot of mathematics. However, we will try to reduce the mathematics and give some more like engineering expression or engineering feeling about that so that we understand what is really happening. It should not happen like we are treating as a black box. We will try to understand each and everything in much more fruitful manner, engineering manner. Let me start. First thing, as we use the word elastro hydrodynamic. Now first 10 lectures we assumed the surfaces are rigid, they don't deform. Now we are going to discuss something like a deformation of tribo surfaces. So that's why we say tribo elements carrying heavy load with a low geometrical conformity, and it has been shown here that rolling element bearing, or it can be also cam follower mechanism, where the contact area is much smaller. Earlier cases we learned that apparent area and contact area. Now here itself, apparent area itself is smaller, and net contact area will be much smaller. So this is what we call as a geometrical low geometrical conformity, are likely to deform elastically and plastically. In the present lecture, we will be giving more focus on elastic deformation, and we know when the running and starts, or the beginning when the tribo surfaces come into contact, there will be also plastic deformation, and there will be some sort of variation in a surface roughness. Yeah, we are not going to change the surface roughness. We are assuming that process is already over, running in process is already over, or it has changed the shape. But what is going to change here, that whatever the peaks, they are going to elastically deform. This is not a permanent deformation. Under load, particularly that instant, it will elastically deform and give us some sort of a space. So here if this surface gets elastically deformed, what will happen? That time lubricant will get into this, and then effective film thickness will increase, and that's what a tribological phenomena will be improved. That's why we are saying elastic deformation is generally order of film thickness. It increases in a lubricant film thickness. That's why it is very important. Earlier in previous lectures we understood that self-acting film, that's a hydrodynamic film, is a self-acting. Now here under load the surface is going to deform, and that is going to increase the film thickness. It's a very advantageous to the us. So how do we effectively utilize in much more fruitful manner? That's a topic of the interest to us. That's why we are saying the local elastic deformation of surfaces which is causing increase in the film thickness. And we also learned earlier there will be some sort of piezo viscous effect. Viscosity increases under the pressure. Here, because of the low geometrical conformity, applied load or applied pressure is very high and increases more than the 10 megapascal. In the situation, viscosity will also increase. So there are three different methods. One is a hydrodynamic film thickness, which we have learned in previous lecture. Second is a local elastic deformation, which is going to increase the film thickness. And third one is a because of the piezo viscous, viscosity increases. So that is also going to increase the film thickness. So this is a very advantageous to a tribological point of view, but difficult in implementation. Doing a calculation, making a model becomes a little more tedious, and that's why we are trying to bring some sort of engineering methods to understand and this effect elastohydrodynamic lubrication mechanism in much more fruitful manner, effective manner. We have already studied the Barrows relation and Rowland's relation. We say the Barrows relation is good for the lesser than 100 megapascal. Rowland's relation is good for the if the pressure maximum pressure is increasing more than 100 megapascal. This is already we have studied in lecture 7. And we also are going to study about the elastic deformation. This is the delta 1, same thing delta 2 also. That means this sphere under load is going to deform by delta 1 deformation. Often we don't want to deal with a two geometry, we want to deal only with a one geometry. So what is equivalent method? We use equivalent method, we try to calculate effective radius, that means r star, which is effective radius, and we are assuming other one is other components is going to be rigid. That means whatever elasticity, whatever the curvature effect, we are going to transfer to the one surface. That means here the component 2 will have effective radius, and that radius will be different than R1 and R2, which can be given as a harmonic combination of these two. And second thing is that even this surface will also get effective elastic modulus, which we need to calculate. How do we calculate? We are going to discuss on this. But elastohydrodynamic lubrication, we don't deal with both the surfaces. We make equivalent surface, equivalent geometry, and other surface will be something like a flat surface, and then it is rigid. So it is not about the surfaces are elastic. We are making one surface or one component elastic, other component inelastic or rigid, and we are transferring, we are changing a geometry, we are changing the Young's modulus or elastic modulus in a manner which becomes effective. That is why we use the word effective radius and effective Young's modulus. Now question comes, how do we calculate this delta 1? That is a simple mathematics. We say this delta 1 is basically CB, this is the distance BC or CB, and that's what has been given here, and that will be OB difference minus OC. This is what has been written. We know OB is a R1 for the sphere 1. Now coming to the OC, this OC can be given as a O square, OA square minus AC square, square root of that has been shown here. And now substituting the OA as a R1, and here there is the semi width or half width of the Hertzian contact. Whatever the contact is getting formed over here, this to this, it is equivalent to 2b. So we are considering b as a semi contact, a semi contact length in this case. So that's has been mentioned here, delta 1 is equal to R1 minus square root of R1 square minus b square. Now we know very well that it can be simplified. We have taken R1 common. This expression can be given 1 minus square root of 1 minus b by R1 square. We can do a Taylor series expansion, and then we assume here that b is very negligible compared to R1. In the situation, this expression can be simplified in something like this: delta 1 is equal to b square divided by 2 R1. Assumption is there, the b is far lesser than R1. It can be 0.1%, it can be 0.2%, something like that. If that doesn't happen, then this theory will be invalid. So this is very important to consider. The B1 is a far lesser than R1. In the situation, delta 1 can be given as a B square by 2 R1. Question comes, R1 I know, but from where the b will come. So we are going to drive those expressions. Now this whole process is called a Hertzian contact. Whatever we are calculating the 2b, it is a Hertzian contact width, that's a 2b. Now in Hertzian contact, we know this, unless has been shown some rolling element bearing, and this is a sphere and this is the race, and then in a race ball is trying to rotate about its own axis, and then there is a film thickness in this zone, and then we are assuming there is elastic deformation plus hydrodynamic action. Both the things are happening in this case. That's why we write motion of one or the both the surfaces. In this case we can assume both, but are equivalent surface also, like v1 minus v2, or if they are rotating in opposite direction, it will be v1 plus v2. So motion of one or both the surface causes fluid to enter in a converging zone. So this is a converging zone. If it is rotating in this direction, it causes a lubricant to get into the converging space, and because the contact patch is very small, that is where the high pressure is generated. And another one point is that if we compare the bearing, which we studied in a previous lecture, in that case bearing length in this case is shorter, and that's the trend. Bearing length we don't keep very large, because effect of the bearing length is lesser compared to diameter. Diameter is much more sensitive compared to bearing length. That's why we prefer to use a smaller length bearing, and here it has been given that way. Another thing, as the pressure increases, so fluid viscosity will increase also exponentially, and it can maybe 2 times, 3 times, 4 times. So naturally it will augment the load carrying capacity. That's what has been mentioned in this case. One interesting point comes particularly when we are thinking about Hessian contact. This graph indicates very good calculation. At a 6% load, film thickness is being given as this manner, and 100% load, film thickness is not changing significantly. That means you can see that this gap is not a very significant. But what is it happening? The contact width is continuously increasing. Maybe initially contact width is 2b bar, something like that, which is smaller than 2b. And when we are increasing load from 6% to 100%, and this is a contact and the width 2b here, I am assuming here. So this 2b is not that very high compared to 2b bar, but load carrying capacity has increased 16 times. So that's our beauty of elastohydrodermal lubrication. With elastic deformation, load carrying capacity enhanced significantly, and that's why we want every tribal surface should run in elastohydrodynamic lubrication. It gives a minimum coefficient of friction, it gives a minimum wear also. Now we have considered sphere. In this case has been shown sphere 1, sphere 2. However, it can be roller 1 and roller 2 also, and then we can drive expression. One important thing is that we will be assuming in all the cases there is a parabolic distribution of the pressure. You can see the contact width at the edges of the contact width, it is a 0, pressure is 0 or gauge pressure, and at the mid value, and this is a total 2b, at the mid value it is a 2, is a p maximum. So we will be considering is a parabolic distribution of the pressure, and pressure will be maximum at the center of contact width. Now what we really require to drive the what will be the value of b, and how do we get the b in terms of diameters, in terms of force, and this is what we need to drive. And as already assumption was, as I mentioned, that we will be assuming the pressure distribution as a parabolic distribution, and thus r can vary from 0 to b. That's what has been mentioned here clearly, that r is 0 to b. Now if we try to integrate and to find out the load, this f, how do we integrate the p, dx and dy, or maybe say r theta into dr, and then we integrate pressure, and the theta varies from 0 to 2 pi and r varies from 0 to b. This is what we can integrate, substitute the parabolic distribution assumption, and then integrate. The results will come something like that. Force is equal to 2 by 3 pi b square into p maximum. Here force is already known. We can either derive the expression of the b or p max. So here we are using the word p max. P max will be given as a 3 by 2 force divided by pi b square. B is a kind of radius, maximum radius of the contact patch. That's what we can derive from this relation. Now we bring the some sort of elasticity equation. So that's why there is a book, Theory of Elasticity, and then everybody must have studied the Timoshenko book, and we say that a local curvature can be given by the square root of 3 coordinates. The shear modulus can be given g as a E by Young's modulus divided by 2 in bracket 1 plus Poisson ratio, and this is a deformation which has been given over here. This is what we want to derive the expression, and this expression in Timoshenko book has been given in the form of f divided by 4 pi g z square and by rho cube 1 minus the Poisson ratio divided by rho. here we want the deformation on the surface, not a subsurface, and we are seeing the z coordinate is along the radius direction, or maybe from a soft surface z to the center side. That's why we will be using z is equal to 0 on the surface. That's why this expression is 0. And then here we are assuming again z is 0. That's why the this rho becomes square root of x square plus y square, and we know x square plus y square is equal to r, which will be varying from 0 to b value that has been given in this form. This is what now next expression for the elastic deformation is being derived. One point comes, and previous expression we say this delta is equal to b square by 2 r1. Now this r and this r will be different. This r maximum value will be b. So this, you should not get confused with this. Reason being, this r is here, which is varying from 0 value to maximum value b. So we should not get confused with this r and this r1. Often the student get confused with this. There are two different expressions. Now we will try to utilize this delta 1 expression. We say 1 minus nu square into f divided by 2 pi Young's modulus into r, which will vary from 0 to b. Same thing can come from elastic deformation of the second sphere. Now we can integrate, because we know the f can be given in terms of the pressure, the way we already derived in previous case, and that has been given. And then there is a axis symmetry, that means 0 to pi value will be can be given exactly, because if I integrate this 0 to 2 pi, this theta and d theta becomes a 2 pi. So that's why we are writing in this manner. And further simplifying, it gives a delta 1 is equal to 1 minus nu square divided by 2 E1 P max, and of course this expression with limits b and 0. If we solve this, what we call the delta 1 is equal to this expression. Now delta 1 is equal to b, again we are bringing a semi width, 1 minus nu square P max divided by 2 E1 into pi by 2. And then same expression can be done for the delta 2. We sum up and this expression comes in this manner. Now we substitute the P max, which we have derived in previous relation, that was a 3 by 2 pi and 3 by 2 f divided by pi b square, and then we substitute, this comes like this. Now if we write the expression of b in the here, that's what comes from here. So that expression of the b also can be substituted, it will come in this form. Cube of the semi with b can be given in terms of effective Young's modulus. This is a effective Young's modulus and this is a effective radius 1 by r. So that will this expression can be simplified. To understand what I mentioned in my previous 6 slides, I have considered one example. We are saying there is assume there is a thrust ball bearing, and this has been given here. Thrust ball bearing looks like something like this. It has 7 roll balls. You can see here 1, 2, 3, 4, 5, 6, 7, and that's why we say it has been given. It has a 7 balls, and every ball has a radius 5 mm or diameter 10 mm. It is subjected to 700 Newton load. We are assuming it is equally distributed. That means each ball will be subjected to 100 Newton load. That's what we are certain. Assume load is equally shared by all balls. And the race is a flat surface here. That means R2 has been given as an infinity. Earlier we were trying to make a surface flat, and that's why we used to write 1 by r star is equal to 1 by r1 plus 1 by r2. Here r2 is already flat being given, I mean I don't have to change. Whatever the ball radius, that will turn out to be effective radius. And now what we want, determine the size of the contact patch on the race, and here the Poisson ratio has been given, because the Poisson ratio still comes more or less 0.2728. Young's modulus also being given 207 gigapascal, which is also kind of established, and this expression has been given only for the comparison purpose or understanding what we have done in previous case. So here what we are saying, load has been calculated. Load on each ball is 100 Newton. 700 divided by 7. And effective radius, we already have mentioned that it will be the effective radius of ball, which is when you substitute in this relation, it comes out to be this, r star is equal to 5 mm. That has been derived. Now coming to the effective Young's modulus, we can calculate. Here you can see here 1 minus nu square divided by u1, 1 minus nu square divided by e2. Effective Young's modulus comes out to be something like that, 1.123 10 is to 11 Newton per meter square. Gigapascal, it will be 112.3 gigapascal. That can be calculated. Now here we can substitute value of r star, value of E and value of F. That gives a value of B, and when we calculate the value of B, it turns out to be 149.5 micron. And here the question says that what will be the contact patch. Naturally contact patch will be 2 into B. So if I multiply 149.5 into 2, it will turn out to be 299 micron. So this is what we are drive, and then we are coming finding the value of the contact patch 299 micron. Now if it is a more, then theory will be slightly invalid and we need to do more iteration, come up with a more rigorous theory. However, this gives us some sort of impression to us. As I say, this is approximation, it's engineering approximation, and many times we start with engineering approximations and try to refine that model. Now maximum pressure can be calculated because already we have found the B, F is already given to us. So it turns out to be 2 gigapascal, and we know that piezo viscous effect will be significant, reason be that the pressure is coming at 2 gigapascal. Of course, when we need to write a pressure distribution, not only P max, and then solve the complete equation. That's very important. Another one, what will be the delta 1, which we assume the delta 1 is almost negligible compared to radius, and that is coming out to be 2.235 micron. So here radius is a 5 mm. You can see here delta 1 is something like if this is a ratio, if we say in this case r is a 5 mm and maybe say 5000 micron, and this is only 2.235 micron. So if this is a much smaller than R1, then we say the assumption was valid and we will go ahead with this. And we are also at the beginning we say elastic deformation is kind of equivalent to the film thickness, that will be minimum film thickness, that is equivalent to the 2 micron or 2.3 micron. Now we talk about the cylindrical surfaces, spherical surfaces. There will be similarly cylindrical surfaces. In cylindrical surface, again we can assume that the pressure distribution is a parabolic, and here instead of one axis we will have a two axis, x and y direction. And then question comes, do we really go ahead? Mostly we have found the pressure distribution in a y direction will not be that significant and it can be easily neglected. So for simplicity, we say pressure distribution is again in this case it will be P max square root of 1 minus x square by b square. Earlier we assume r by b square, here we are assuming instead of r we are assuming the x. So that's not a very big difference. Force can be calculated by integrating the pressure expression over dx and dy, and we say that dy is not changing significantly, so whole expression turns out to be into the L. And then we substitute these values and then integrate, and then finally this expression turns out to be f is equal to pi by 2 b L P max. That's what has been given in this manner. And we solve, we say for the pressure, we say P max equal to 2 F divided by pi B into L. That means if the length is increasing, P maximum will come down. If patch B is increasing, then again P max will come down. While F is increasing, the P max value will increase. This can be used for the roller bearings, earlier expression for the ball bearings, but this can be used for the roller bearings and gears also. So this kind of expression can be utilized. easily. There will not be much problem as such. Now we talked about something about elastic deformation, but the lecture title itself is elastro-hydrodynamic. So we cannot omit the hydrodynamic action. We already have discussed elastic action, but now hydrodynamic action. Earlier in a previous lecture, we derived the maybe we presented this Reynolds equation, and various terms were defined, u value and b value. This is what we call also a stretching term. We also describe something like a squeezing term, squeeze out term, and then we also say that for hydrodynamic action we really require a wedge action. If we simplify this expression and then maybe categorize, what we studied earlier is something like a isoviscous rigid surfaces, where viscosity is also not going to change. Then second comes a piezo-viscous rigid, the elastic deformation is not considered, but the piezo-viscous effect, either we consider the Barrows relation or Uland's equation and incorporate the in Reynolds equation. That means this expression should be utilized over here, or this expression should be utilized here. That means we need to integrate with in terms of pressure. It's not a constant. So while in case of isoviscous rigid case, eta can be treated as a constant and will come out. Another one is isoviscous elastic. That means viscosity is not going to increase significantly, but surfaces are elastic, like a rubber surface, like a polymer surface. They are going to deform, but viscosity effect will not be significant. So that in the situation is what we could use the word isoviscous elastic, and this is the final one. We say the piezo-viscous elastic one. That means there will be elastic deformation and there will be piezoelastic effect also. Both the things will come or will be necessary to incorporate. And then here for simplicity we are taking assumption. We say that velocity in z direction is not there. That means this term is equal to 0, and then the squeezing velocity is not also there, so this term is also 0. Only in the first term is there, again only there is a one velocity u2 or u1, or we can say the u. This is what has been mentioned. This is a simplified Reynolds equation, where when we are assuming this tangential speed in a z direction is not there, tangential speed is only in a x direction, and there is no squeezing term. Now further we can simplify. We say that in this situation h is also not a function of z. That's what has been given. H does not depend on z. In this situation h can be brought out, and that has been given here. And then viscosity, because we are trying to go ahead with the piezo-viscous rigid expression, this is what we are trying to bring. So piezo-viscous rigid effect, eta value can be substituted, and that's what has been given over here. We are substituting eta 0 into e power alpha p. We are assuming the pressure will be lesser than 100 megapascal. If it is a more than, we need to bring this Rowland's equation. However, it will increase the mathematical complexity. That's why for trying to understand initially how piezo-viscous rigid effect can be calculated, that's why we are bringing this simplification. Now one more, we say that u also does not depend on x. It's not elastic surface, because if there is a rubber, and even x direction velocity will change because of the elasticity. However, we are assuming the surface is not elastic one, and u will remain constant, the same value at the different value of the x. So that's why we say assumption u does not depend on x. With that, what we are going to do, this u will be brought out, and that has been given in this form. So we are rearranging the complete expression. You can see here we have a rearrange in e to power minus alpha p here, e to power minus alpha p here, and trying to solve this equation. And this is what has been given first term. Second term, you can see here h has been taken out, it doesn't depend on z. I have a pressure variation in z direction we are considering. The viscosity at the atmospheric pressure has been provided. Velocity is not a function of x that has been given, and we are trying to solve this. Now one interesting thing is that if we substitute q is equal to 1 minus e to power minus alpha p divided by alpha as a q, and we will get this term. dq and the dq by dx e to power minus alpha p dp by dx, obviously the dou pi and dou p by dou x, or we can use the word del also. What we say, that del q divided by del x is equal to e power minus alpha p del p divided by del x. That can be given. When you write this in this form, this is a very simple form which we were solving for the isoviscous rigid case. Now similar form has been brought up for the piezoviscous rigid form. That's why the Barrows relation is important to understand, and it really consider the piezoviscous effect, only that it becomes inaccurate when the pressure increases more than 100 megapascal. But it provides engineering sense, that's why we are considering. Another, as I mentioned earlier, that 1 by r star will be given as a equivalent radius, and this is a r1 plus r2. Now to understand this, I am taking one example which has been given in my book. What has been considered there, bearing radius, we are assuming sliding bearing, 25.3 mm radius, length has been considered, radial clearance has been given, general velocity, oil viscosity, and we are assuming instead of, we already considered in that lecture that every bearing problem is inverse problem. Mostly the load is given and eccentricity will not be given, and we need to calculate. So instead of going for those iteration, for this case we are considering the eccentricity itself. We are not going to calculate the load, we are going to calculate only what will be the P max and how it is getting affected with the viscosity. So this is this a complete example has been given in my book, and it has also the MATLAB coding. You can directly use that MATLAB coding to see the same results. And this is the geometry we are considering. This is the journal, and of course is the hollow journal and the bearing surface R1 and R2. When we try to solve further this data, we find there is no difference, pressure including viscous effect or actual pressure. It is coming out to be a maximum pressure as a 1.5 megapascal, which is not really significantly different. So that means if pressure is a lesser, we don't have to consider any effect. In my view, the overall pressure lesser than 10 megapascal, we don't have to consider the rigid effect or the flexible or elastic surface or piezo-viscous effect also, unless the surface is a rubber material or kind of polymer. Here the both the surfaces are made of the steel, so they really do not deform, and viscosity also effect will not be significant. But to do a parameterization to see if I change the viscosity, instead of 10 millipascal second, if I make a 200 millipascal second, what will happen? Similarly, what will be the effect of the velocity? Instead of 20 meter per second velocity, if I make a 50 meter per second, what will be the effect? So this is we can do some sort of parameterization and understand what is really happening to the bearing performance. So that has been done in my next slide. Here we are saying there is a hardly any difference between the maximum value of pressure and lesser than 10 megapascal. There is no point to really consider these effects. Now in next effect, we say that instead of 10 millipascal, we have increased the viscosity as a 200 millipascal second. Again, eccentricity has been kept the same. It will increase the load carrying capacity significantly. As I say that we are assuming direct problem, we are not solving as an indirect problem. This is only for the understanding purpose. So in the situation when we increase the viscosity, and if we don't consider the piezo-viscous effect, then the maximum pressure comes around 30 megapascal. But if we consider the piezo-viscous effect, it comes around 36.5 megapascal, where there is some sort of variation, almost 20% variation is happening to the pressure when we are increasing viscosity or using the thick oil, and that has been shown a maximum value difference. Of course, in my book we have also given the 3-dimensional, but for this lecture I am using only 2-dimensional case. Of course, the pressure, the expression which has been solved for the 3-dimension, for illustration purpose, a figure which I am providing, this is only 2-dimensional. This doesn't mean that we have neglected one pressure variation in z direction. We have considered the pressure variation, but only we are showing in a 2-dimensional and not a 3rd dimension. So this is a comparison of pressure along the central plane in of the axial line. There's the mid plane of the bearing at the center of the bearing, and this complete expression with including the MATLAB coding has been given in my book. That's a fundamental of engineering tribology with application, which was published in 2016. Complete MATLAB code also has been given in that. Now, as I mentioned that we increased 200 millipascal second viscosity, which is quite huge. Now, another hypothetical concept, we say that now suppose instead of velocity keeping 20 meter per second, we want to increase velocity also to 50 meter per second. In the situation, we are able to see there is a significant difference. So, increase in viscosity has a some effect, but increase in velocity also has a significant effect. So when changing the velocity by increasing velocity by 2.5 times, we are able to see instead of 68.87 megapascal pressure, it has reached to the 116 megapascal pressure. So this is a reasonable, and then you can see the plot here. Blue color pressure is with a piezo-viscous effect, and red color is without piezo-viscous effect. So this is some sort of understanding that what is really happening. Earlier we considered only the elastic deformation. We took a example of the ball bearing, a thrust ball bearing. Now we have considered another example which has been quoted in my book, and then now we are trying to understand what will be the effect of the viscosity and what will be the effect of the velocity on piezo viscous rigid surfaces. So these are the important thing, and we solved this Reynolds equation, which as I mentioned we are using the Taylor series expansion, and sometimes you use a word a numerical difference method or finite difference method, a central finite difference method. This is for the first derivative and this is for the second derivative. And then of course we took a coordinate this matrix of n into m. Whole bearing surface was expanded, and it was given n into m. Only the problem comes over here, initial pressure guess. We generally assume the pressure initially is 0 or equal to 1, whichever method you try to use. However, if there is some approximation or some analytical expression that can give a much closer result to the real value. So we want to really look at first thing some approximate solution which provides engineering guess also. It should not turn out to be only mathematic, or by increasing 5 times I am getting this, but what is the expression. So this is what we are trying to solve using some sort of equation or some sort of expression which gives us some engineering sense to us, instead of just looking at the f of x or on the first derivative, second derivative, something like that. It should not turn out to be the black box. It should turn out to be a more like engineering solution to us. For that, Ertel-Gruben equation is a known equation which is started accounting there's a Hurgen theory, that means bringing elastic deformation and piezo-viscous. So we started lecture with the Hurgen theory, elastic deformation. We consider one example. Again, second example we say piezo-viscous but rigid. Now we are coming to the Ertel-Gruben equation, which he has incorporated Hurgen theory as well as a piezo-viscous effect both together along with a hydrodynamic lubrication. So this is a very interesting for understanding purpose, but if come think from accuracy point of view, that is not good. Accuracy of Ertel-Gruben equation is not going to give a really very good solution, but it provides an engineering solution. And then obviously the machine learning, if we have a guided the solution, that's like a Gruben equation kind of solution, we can improve the accuracy. That's what I'm trying to project. So in this situation, we are again considering only one dimensional equation instead of two. Earlier we considered this expression also when we use the finite difference method to get a solution. Instead of that, we are considering only one dimensional equation, and the del q by del z has been rejected. We say that there is no variation in this direction, so only this expression is being considered here. Of course, in this case we have already incorporated the Q, and then which is a reduced pressure which incorporates a piezo-viscous effect. Now we need to bring elastic deformation. So the Grubens equation, without elastic deformation we do calculation something like that, but in under the plastic deformation we know the Hudson that contact width will be equal to 2b. They assume that this H0 minimum film thickness or central film thickness will be varying from one point to other point. That means instead of only the one point, the center point, this value, it will have a starting from 0 to maybe say 300 micron or maybe 200 micron, depend on the value of the B, right? And then we are assuming the film thickness in this region will be constant. So it is not only the conversion, we are assuming there is a conversion zone, but after that there is a stationary kind of zone, and where the pressure only gets develop and significantly high, where the piezo viscous effect also happens. So that's what his assumption, and he tried to give a solution based on that. Now this is what we call a long bearing solution, and for long bearing solution we assume that pressure will be maximum at the some film thickness, and for when pressure will be maximum, or in this case reduced pressure will be maximum at some film thickness, this gradient will be equal to 0. That's a simple optimization problem, and when you substitute and we get an expression something like that, del q by del x 6 eta 0 u, this is the same thing, and then at h bar this will be equal to 0, and that can be given h minus h bar divided by h cube. Now this is what I'll be given on an overall film thickness, which we were doing earlier for the only hydrodynamic case. Here it will be summation of 2, what is the Hertzian contact film thickness, and what is the film thickness outside the Hertzian contact. Of course both will depend on geometry, whether it's a roller or roller, or cylinder or cylinder, with the convex concave geometry, convex convex geometry, but film thickness can be given as a S0 plus HS. S0 is for the Hertzian contact, and this is HS is outside the Hertzian contact. And when you substitute these values in this expression and simplify, what we get, del q divided by del x is 6 eta 0 u hs divided by h0 plus hs cube, and this minus. So instead of this expression, you can see now this expression, which is also incorporating the Hertzian expression or Hertzian film thickness. Now this can be simplified, and there is a good book, Cameron's book in 1966, which has derived all expressions, and then they have given HS the way we have derived in previous slides. The effective Young's modulus into P max into B. B is same Hertzian contact width, 50% of Hertzian contact width, and some expression along with that. And then this complete has been given as a equivalent modulus. That's why it's been given in this form. If we further simplify by substituting the value of P max, because we already know that for the long bearing approximation the P max can be given is equal to 2f divided by pi BL. That was we already derived in slide 8, and then we can substitute this values over here. By substituting, it can get this results. Now one more thing comes in non-dimensionalization, because we have many different geometries. So it is when we are going for the more sophisticated calculation, it is always advisable to go with a non-dimensionalization, because the calculation error will come down significantly, because sometime r is in mm, sometime length is in mm, and now sometime this mm becomes a meter, or some becomes sub mm, or maybe say few microns. So there is a huge variation. So that's why we say non-dimensionalization. Now you can see here non-dimensionalization. What we have done, this whole expression has been brought to this side, and that's why we are saying hs bar is equal to length by effective Young's modulus hs divided by f, and this is a complete expression over here. This is a non-dimensional expression, and then Cameron has simplified this also. You can use our thing h bar, hs bar is equal to 4.2. In this case x will be more than b, because this expression has to be positive. That means whatever this film thickness is for the not Hertzian contact, it's outside Hertzian contact. Let me repeat, Yeah, in this case, this is HS, which is outside the Hertzian contact. Hertzian contact H0 is already known to us from a previous expression. So here we are trying to figure out what will be the HS. Naturally, X will be more than B, because it has, in that situation only it will go out. This is what we have been trying. Now HS is just outside the Hertzian contact. Film thickness where the X can be need to be greater than B, it cannot be lesser than B. In lesser than B, this sum will be negative and then it will become invalid. So X has to be greater than B, and this whole term need to be positive, and HS can be given in this form. So this is a what Cameron derived, and he used the word all in the plumb thickness in normalization method. So HS is outside the Hertzian contact, H0 is a Hertzian contact, and then when we simplify using this relation, and of course again he has done the normalization of the X value also divided by B. Overall, after non-dimensionalizing, Q becomes Q bar into 6 eta 0 U B divided by F L pi E star square. Now this whole expression turned out to be much simpler compared to this, and this is what has been given in the form. Now this is what I am showing, that the 1966 Cameron book has given this call up expressions. So del q0 and then del q bar divided by del x bar is equal to hs bar divided by h0 by hs bar. Now this has been given, and then if we want to do only hydrodynamic, we don't want to go with a Cameron relation. So that case only the major issue will come only at the x is equal to minus b, that minus b or plus b when we are entering or exiting. Earlier before that it is a simple hydrodynamic, we can go ahead with expression, and Hertzian is also none. Only in the transition case this expression will be required, and then he has a drive this relation in this form. That means alpha can be given in form of the h bar, the h0 bar, and then there is a negative term on this. If you further simplify and rearrange, this is a real equation, that h bar and the h0 bar can be given in terms of 5.91 eta 0 alpha u b f L pi E star bar. Now this is where we are getting from those equations which with help of the Cameron book. This is already we know. We substitute this value, we get a very complicated expression. Now, after this, what researchers have done, they try to solve this in a much simpler manner instead of going for those so many complicated cases. Keeping same model, similar model, they drive the expression which are much more accurate compared to this. So they have done normalization H0, which is a minimum film thickness in Hertzian contact or elastic deformation, and then into R star equal to 2.65 G parameter, U parameter, W parameter. What are G parameter and W parameter? G parameter is known as a material parameter. Now researchers have divided slightly different manner. They say calculate separately material parameter, calculate separately speed parameter, calculate separately the load parameters, and you calculate also effective radius. Now what is a G parameter? Is a alpha piezo viscous coefficient into effective Young's modulus. Sometimes people use a E star and sometimes they write a E prime. Similarly, speed parameter, this is the velocity, this is the viscosity, is again effective Young's modulus is R star. W parameter, the applied load, E the prime, L and R star. Now, if I try to similarize, we say in this both the cases expressions between the Cameron and what people have done here. Here we are replacing F, which was a drive earlier, with a W. So W replaces F. Here the small u replaces a capital U. Similarly, mu replaces a eta 0. So this is the only difference, and now these are the well known what do you say, the engineering calculation for the elastro hydrodynamic lubrication. particularly for the cylinders, which we can use for the gears, or we can use for the rolling element bearing or roller bearings in the case. Now coming to for the spherical bearing, similar expressions are available. That's why I said again is a normalized expression H0, that's the minimum film thickness in a point contact or a spherical context, divided by Rx. Again here is speed parameter, this material parameter, a load parameter. This is coming from a two axis, because we know in a point contact it will not be spherical contact, it will be elliptical contact. So it depends on the ratio, and that is where the elliptical value of the K comes, which is a ratio of Ry by Rx. To understand all this, let's consider one example. We again considering the one ball bearing, which is something a 6210 ball bearing, which has a 12 mm diameter of the ball. Earlier we assumed 10 mm, now here we are assuming 12 mm, and then we say maximum load, because in the radial bearing maximum load will be, if the load is applied, maximum load will be the bottom roller which is coming into contact. Now Young's modulus is also being given 202 gigapascal. Pressure viscosity coefficient has been given. Again these are the we are giving values for the understanding purpose of whatever we have derived is correct or not. Dynamic viscosity eta 0 has been given. Radius of the inner ring has been given 28 mm, and its a groove in perpendicular direction is 6.5 mm. So in a rotating direction it is at 28, and tangential direction or perpendicular direction, axial direction, it is 6.5. Now this 6.5 need to be slightly bigger than the ball radius. That should, because the race has to accommodate the ball. Naturally the radius of the groove has to be more than the ball radius, otherwise it will not get accommodated, it will not get fit into the slot. So that has been given. RPM of the shaft which is rotating in a bearing, or that is around 900 RPM. And what has been asked, what will be the minimum film thickness, because many times we say that whether it is a EHL case or a mixed lubrication case, that way you require a mixed lubrication, the minimum film thickness, and based on the minimum film thickness and we take this expression, we figure out what is the value of um, specific film thickness. If a specific film thickness is more than 2 or 3, then we say it is a EHL, otherwise it is not a EHL, it is a mixed lubrication. So using this we can calculate first what is the velocity. U has been calculated something like 2.639 meter per second or 2639 mm per second. That's the first calculation. Then if we try to calculate the effective Young's modulus, it turned out to be something like of course in this case instead of meter we are giving in mm, because it is easier to calculate all the things in mm. That's why it is coming at a 1.0959 e to power 5 or 10 raised to 5 Newton per mm square. Now based on that we can calculate the material parameter or G parameter. This value is already being given, this value has been given. You can see this complete parameters are non-dimensional. So all the expression which we are writing here, everything is a non-dimensional. That's what the article equation was mentioned, or Cameron, everything we are trying to do non-dimensional, so that results are easily calculatable and we can really get a quick results. Now coming to the Rx, when the ball radius will be same in both the cases. However, ring radius in the circumferential direction or rotational direction is 28 mm and perpendicular direction is 6.5 mm. So we need to really calculate effective radius in x direction and effective radius in a y direction. So effective radius in the y direction is turning out to be 3.12, while effective radius in x direction is turning out to be 4.9412. Electricity parameter is somewhere the 0.7674, and then if we find out the load parameter is turning out to be again non-dimensional number 5.606 10 to minus 4. And then based on again then we will calculate the U parameter is turning out to be the 5.5 10 to minus 11, and then overall H0 by X is turning out to be 3.63, velocity G W and this one. Now substitution what we get, as 0 by Rx is equal to something like 1.1086 10 to minus 5, and then film thickness as a something like a 0.054 micron, which is very very small. Now if the surface roughness is much smaller than this, then this will work nicely in a EHL case. The surface roughness is in something like a itself a zero point 0.1 micron, then this is a mixed lubrication or boundary lubrication. So this is where the after doing calculation we figure out whether whatever the assumption initially we assume, the two surfaces will be completely separated because of the viscosity effect, they are not getting separated, then there will be issue. So this is what continuously need to be solved, so the overall impression we get, and we try to get a right results. Now we are doing this kind of calculation, and then we will try to improve this model using the machine learning, but it gives a really good engineering solution to us. Thank you for attending this lecture. Thank you.